Is this exciting? Okay, here we go. So should we start with the khutbah al-hajj or something, I think? So can we turn the light, please? So linear search versus binary search is what we're talking about today. Last time when we introduced the topic of data structures, we talked about how we will perform many operations on these data structures. Insertion, deletion, this, that, merging, sorting. We also mentioned searching, and we said that some searching algorithms are fast and some are not as fast and can be very slow. So today is linear search versus binary search. The first searching algorithm we cover, linear search. This is something already all of you know, and you learned linear search in 202. So if you want to search through an array, you already studied this. What do? You start at the beginning of the array, yes? Index 0. If you have 100 values in your array, you start at index 0, and what do? You iterate, you loop through, you traverse, we used the word last time, but you iterate through your array. You start at index 0, and you go hatta index 99. You're looking for the value 12. You go to index 0. Are you 12? No. You go to index 1. Are you 12? No. Go to index 2. Are you 12? No. And you keep going all the way until index 99. Are you 12? No. Return false. Not found. واضح? Who's with me? Or you go through, start at 0. Are you 12? No. Are you 12? No. Are you 12? No. Index 4. Are you 12? Yes. Return true. So you can return true. You can return false. You can return the index where you found it, because maybe that is important for the purposes of the search. Depends on what your program, the requirements of your program. So this is the basic idea of linear search. Okay. So if we see the value you're looking for, return true or false, return true, or return the index. If you don't find it, you could return false, or you can return what integer? You cannot return a positive integer, because positive integer, ma'ana, the index where you find it. Command 0 is an index. So if you return the index where you find it, if true, if it's false, what do you return? Minus. Well, minus 1, maybe. Minus 100, it doesn't matter. Any minus, right? Because that's an alama. No index can be minus. Therefore, it's false. We did not find it. So this is the idea. And this would be your code. You should not need a big explanation for this code, because it's a basic for loop. It's a search method. We send to the method 2 parameters. The first parameter is an array, A. The second parameter is an integer, ismuhu value. We're looking for this value, 12 method. So we have this for loop. We iterate from the beginning of the array, which is index 0, all the way until the end of the array, which is what? The a dot length, this is wrong on the slide, a dot length minus 1. Okay, so if someone emails me, I can correct this. A dot length minus 1. And of course the new increment. So what we do is we simply check. If ai, the value at index 0, if it equals 12, return true. If it does not, what do? You come to the loop again. I plus plus I is 1. If a of 1 equals 12, return true. If it does not, come around, loop again. I is 2. If a of 2 equals true, return true. If a of 2 equals 12, return true. And you keep doing this. If it's true, you return true, and the method will exit. You return true to main or to the calling method. Here, if it does not return true, it does the entire loop. It goes from index 0 until the end of the array, does not return true. What happens? We return false. واضح? Is that easy? Who follows? Clear? Okay? So this is what happens. Basic linear search. So the code I say here, as mentioned, it returns a boolean, true or false. This works. This is acceptable for most purposes. But often you will want to use you will want to know where is the index of the value. Maybe you want to access the value. So another thing is simply to return where you found the value, as mentioned. So you can return, we found it at index 7, مثلا. Okay? So here's the same code, but here we return an integer. And if we don't find it, we return a -1. Same code, this time we return an int, and instead of returning true here, if we find it, we return I, the index into the array. Which index? Where we find the value. مين معي؟ 100%? Who's with me? Hands, I want to see. Okay? You're not with me? Little bit. You have question? Just again, this is the same code as last time. What's the difference? Saluka. Where's -1? What? No. This had return true before. Now it says return I. Because what are we doing? Before, if we find the value, that's the if statement. If a of I equal 12, مثلا, the value, we return, من قبل, we return true. Now we say something different. Now we say we can return the index. Which index? The index where we find the value. Are you with me? The index where we find the value. We return it. So in main, inside your main, if the value that is returned, if it is 0 or bigger, we know we found it. If it is less than 0, مثلا -1, we know we did not find it. Okay? So it's the same thing, but it allows you to return a specific index, so you get the benefit of the true-false, but now you have more information, right? So this is truly better, but it depends on the requirements of your program. Yes?
I think we break after return I.
Where? After return I, you do not need a break. Because once you return, the method is done. Once you will break, what does break do? Break exits you from what? From the loop. Return, khalas, exits you from what? The method. Okay? So if we want to do an analysis of this code to see how long it takes, we say if the array is unsorted, this algorithm is optimal. You cannot make the algorithm faster if the array is unsorted. Because if it is unsorted, you must look at every value. Aswal hal. All during the semester, I will say aswal hal, worst case, worst scenario. Okay, worst case is what we always talk about in this class. The only way to be sure that a value is not in the array is to look at every single element, cell of that array. Just like if I give you 100 test papers, 100 exams, and I say find the exam for fulan, and it's not sorted. If you look at just the first 10, can you say dhaman, it's not here? How can you can say dhaman, it's not here. What must you do? Sorting's even longer, but what's the easiest thing to do? Just check all of them. Right? If I give you 100 exams, you want to know is fulan there, it's not sorted, you must just go check each one. So aswal hal, he's the last paper, or he's not there. So if I give you 100 exams, the best case, it's on top. Right? It's right there at the front. But the worst case is it's not even in there. And you have to go search everything. Right? So this is the idea of the speed. Same thing here, same as last case, same as if it was the last one, but if it's not there, it's even one worse, because now you have to skip the last one, right? So, the only way to be sure that the value is not in the array is we must look at every single value. And so now we ask a question, the question being, can this be faster if the array is sorted? And the answer is yes. It can be much faster if the array is sorted. So the introduction to this topic of binary search, because this brings us to binary search. And we introduced this by talking about, I say, the number guessing game from childhood. And I don't know if children play this game in Saudi. The LAB, they tell me, yes, maybe one time. But it's a game for, somebody who's deaf or maybe. So they say, they don't want to play it. They play soccer instead, or football instead. The number guessing game from childhood is where we say, I guess a number from between 1 and 100. I pick a number, and you have to guess the number. You have to find the number, okay? So I have a number between 1 and 100 in my mind, and I want you to guess the number, okay? You make a guess, and I will tell you if the number is too high or too low. Who follows me? Who knows the game? Okay. Can I play with you, Hassan? Okay. I have a number in my head between 1 and 100. Guess. 50. Too high.
25.
Too high.
15.
Too low.
20.
20. Too low.
30.
Too high.
25.
Too high.
22.
That's it. Okay? So what did he do? He did not do it perfectly, but he did good. What did he do? What is the winning strategy? Always divide the ihtimalat in half. So if we play the game, and because what is the goal? Is the goal to find the number? No. Anybody can find the number. I always make a joke. I play with, name? Amr. I play with Amr. You pick a number. Between 1 and 100. Are you ready? It's going to be exciting. Okay? You ready? You have the number? 1. 2. 2. 3. Billah. 4. 5. Will I find the number?
Yes, eventually.
Will I find it? Yes. But is this the hadaf? The goal is to find it fast. So the proper way to do it, now we're going to play it properly. Pick a number again, a new number, between 1 and 100. 50. It's too low. 75. So now between 75 and 100, huh? Yeah. It's too high. So your number's under 75. So between 50 and 75 is 25. Pick half of 25 is 12. So 62. Too low. So between 62 and 75, which is 13, so 6, 68. Between 62 and 68, so there's 6. Between 68 and 75. MashaAllah, but we're back to 50? Yeah, Sheikh. We have a problem with the too low, too high. We were at 68, and you said 68 is too high.
Yes.
Okay, but before this, I said 62, and you said too low. Ba'dain, I said 68, you said too high.
68 is too high.
But 62 is too low, command, sah? Either your number is between 62 or 68. Yes? The translation. Aqal min 62? Aqal min 62? Allah yadik. So you messed it up. We have one more person. Yes? Pick a number, quickly. We're going to spend an hour playing the game, mashallah. You have a number? Don't pick 50. 50.
Too low.
50 is too low, so I need to go higher, so 75.
Too high.
62.
Too low.
Too low. So between 62 and 75?
Yes.
So that's 13 that is between them. So I divide in half, 6. So 68.
Too low.
68 is too low. So between 68 and 75, there are 7 position, right? 7 spots basically. Divide in half, 3. So 71. Okay? So I found his guess within 4 tries. 4 or 5 tries, right? So this is the idea. We want to find it as fast as possible. And what are we doing? We are basically dividing all of the possibilities. So there's something important I talk about from now. It is called the search space. Okay? So what we have is all of these ihtimalat, possibilities. How many for our game? 100. I say pick a number. You have a number in your mind. I say 50. So right here I say 50. You say too low. So the answer must be between 51 and 100. So what did I do? My guess of 50. When I make the guess 50, what I just did is I remove half of the ihtimalat. You say too low. So I say, okay, it must be between 51 and 100. So then I say, okay, 75. You say 75 is too high. So now we remove this half of the ihtimalat. And so now it must be between 51 and 74. Because it's not 75. This is what happens. We're constantly dividing the search space in half. We remove, after the first guess, we remove 50 possibilities. After the second guess, we remove 25 possibilities. This is why it's very fast. If we play the game, and I start by saying 1, what did I remove? 1 possibility. 2. 1 more possibility. Right? This does nothing. Effectively. It's very slow. So this is the idea. So what is the first guess of most people? 50. Okay? Why? Because no matter the response, too high, too low, على أي حال, what did we do? We divide the search space in half, which leaves exactly approximately half of the possibilities. Okay, so this is the winning strategy. Always guess the number that is halfway between your 2 possibilities, to remove half, correct. So the question, can we adopt this strategy? I say adopt, that's fine, adapt, both work. Can we, no, both can work, depends on your intention, but can we adopt this strategy? But specifically it's better, can we adapt, can we utilize this strategy for searching for a value inside an array? Of course, the answer is yes. But what do we need? What condition do we need? Sorted. The array must be sorted. So this binary search that we're going to talk about will be very fast compared to the linear search. But we have one important shuttle. The array must be sorted. This is the condition. Just like the elements, when I say make a guess between 1 and 100, it's sorted. This is why it's fast. Okay? So the array must be sorted. So here is the idea. We're given the following array. Okay? We're searching for the value 19. Where is halfway between in the array? Index 4, 33. So I think this is clear. Because again, we want to search for the value 19. We see that the value is right here at index 2. Clear? So we know it's there. We want to find it using this same strategy. So we first need to guess in the middle. So where's the middle? You said 33, index 4. Who's with me? This makes it easy. Then I will skip the next 2 slides because maybe some people think, okay, well the middle number, here's 2, 118. What is the middle number of 2, 118? 2 plus 118, 120. 120 divided by 2, 60. So 60 is the middle number, but there is no 60, but this is the middle. Is this the idea? No, the idea is the middle of the array, not the middle value, the middle index. But everybody already understood that. You all told me, where's the middle? Index 4, the value 33. So this is the idea, and this is what happens, okay? So where's the value halfway between? The answer is 4. So I'm going to skip this. So we say, where are we at? So the middle is 4. This is what we just said. So the lowest index is 0. The highest index is 8. The middle index is 4. So what we do is we look at this array. I'm just going to come back to the array. We look at the array, page, what is this, 10? Page 10. We say, okay, this is the middle index right here. We calculate the middle. And we're looking for 19. Nas'al. Are you 19? No? Okay. Wait on 19. Is it smaller? Okay. So now I must look from which index to what is range? Mada. What is the range, the mada, from index 0 to index 3 or 4? 3, because we checked 4. We said to 4, are you 19? La. 19 is smaller. So the search space was from index 0 to index 8. We calculate the middle. The middle is 4. And now we say, okay, index 4, are you 19? No. Where's 19? It's smaller. Okay. So now we must look, what is the new range, the meda, from index 0 to index 3. This is the new range from index 0 to index 3. So what do we do now? We need to calculate the middle. How do we calculate the middle? The same way we calculated this 4 as the middle. How did we calculate this 4 as the middle? We said low plus high divided by 2. What was the low at the very beginning? So mid equals low plus high divided by 2, which was, at the beginning, it was 0 plus 8 divided by 2, which is 4. So that's how we calculated 4. So now, we said, okay, but 19 is lower. So now the search space is from 0 to 3. So low is 0, high is 3, 0 plus 3 divided by 2. This is the new mid. So we get 3 divided by 2. The answer for you many students will say 1.5. There is no index 1.5. So we need to give you reminder, tadhkir, from 202. What is 5 divided by 2? Integer division. Al-jawab, 2. Now you think al-jawab 2.5. But delete the 0.5. The integer division. Okay? 5 divided by 2 is, we want the whole number, 2. If I say, what is 11 divided by 2? What's the answer? 5. We want the whole number. So if you have 11, this is like ibtidaiya, right? Divided by 2. 11 divided by 2. 5. 5 times 2. 10. 11 minus 10. 1. Baqiya. Wahid. But we want this. 5. This is integer division. Integer division? Clear? So we want to use integer division, and we say, what is 3 divided by 2? 1. So we calculated the new middle right here, index 1. And we ask the same questions. Are you 19? No. Is 19 smaller? No. 19 is even higher. 3 questions. Are you 19? Yes? Great. No? Tayyib. Second question. Is 19 smaller? No. If it is, great, we found it. If we find it, we know where to look. If it's not smaller, if it's not the same, if it's not smaller, lazim, it must be bigger. So we were looking from index 0 to index 3. This is the middle. We say this is not 19. It's not smaller, lazim bigger. So what is the new medad? From index 2 to index 3. This is the new range. Mimai, the low is 2. So, the low is 2. The high is 3. So we're going to say, we need to calculate the middle. 2 plus 3 is 5. 5 divided by 2, 2. So the middle is 2. And we say, are you 19? Yes. Khalas. We're done. This is how the algorithm will work. Okay? So let us do, I would say let us do one more, but let us actually get to the code. Then we'll do one more example. Okay? So what I just did, the explanation on the board, was more detailed than even with the slide. And so I will skip these pages because I put these here for you to be able to read at home. This is one of the luxuries that we give you in this class by making comprehensive slides, detailed slides that you're not having to take notes like very fast notes and writing very quickly. That you have the ability to study at home. So the example that we just went over is right here. Okay, so I can skip that. So I want you to think about the code before I show you the code. I want you to think about the code. So this is going to be, if I come back to our slide with the array, at the very beginning, think about what we will, you know what, the pen is not working very well, so I would like to change the camera to the screen so I can actually write using Notepad. So let me see, can we do this right now in the middle? It's better what? No, I'm gonna go wide. This is fine? Good. I don't know if you will be able to see this. We'll find out. So we come back and I open Notepad. Make it big. Okay. So we have a method. What is the method? Public, static, let's say Boolean. We return true or false first, but بعدين we can change it. Boolean. And we call it bin search or binary search, as you like. What do we send? We send an array. Call it an array A. Int value. We're looking for a value. Okay? So what did we just do on our example? We're right here. At the very beginning, we need to have a low and a high, right? So we have here, we have int low equals 0 at the beginning, so what is high going to be? High will be a dot length minus 1. That is the high index, huh? Because here, high would be 8. The length is 9. 9 minus 1 is 8. Mimai? Shabab? Okay, good. So we calculate the high, we calculate the low. Now we have a while loop, because we need to keep doing this. So what did we do? We calculated the 4 as the mid. Then we check, are you 19? No. Is it lower? Yes. Then we go lower, and we do it again. We keep recalculating the mid, and we keep asking those 3 questions. That's inside a loop. What is the condition of the loop? Nantadar. Okay? We wait for this. So here's our loop. But what do we do inside the loop? What is the first thing we do inside the loop? We have to calculate our mid. So here I will just put int mid. And I don't even know what the code looks like. I didn't look at the code today. I looked at it last semester. But we will do something very similar together. So int mid, we calculate. So we just declared it. So now we calculate mid. Mid equals what? Low plus high. divided by 2. This is our mid. Yes? So what are our questions? We want to now ask, so what did we just calculate? The middle index of the array. So for what purpose? Because the first question is, basically, are you the value we're looking for? Yeah, middle array. Right? Are you the value we're looking for? If a mid equal value, return true. Easy? Excuse me. غير ذلك, or else if I want to say, I can do it this way, but I like mantiqiyan, I like it on the other way, on the other side. I think it's just easier. If the value is our middle of the array, return true. غير ذلك, if the value is smaller than the middle of the array, we need to do something. Finally, but I did not say what to do. Finally, if it's not the middle, if it's not smaller, it must be bigger. So I like to put this as a comment. Else, ma ma'na else? Else ma'na that the value must be bigger than the value at the mid. You do not need to put this right here, but I do it for myself, so I can see the mantiq completely, miya bil miya. So I have here, if it's equal, do something. Else, if the value is smaller, do something else. Finally, غير ذلك, do something else if it's bigger. So what do we do here, right here, and right here? What do we do? Let us look back at the array. ونسأل, what did we do? ماذا سوينا? Or إيش سوينا? We need to learn. ماذا سوينا, right? With the فصحى. Nobody says that ever then, right? Or إيش نفعل? It's very غريب, right? So here, what do we do? At the very beginning, low is 0, high is 8. We calculate now we enter the loop. We calculate our mid is 4. And we say, are you 19? No. Then we say, is 19 smaller? Is 19 smaller than you? Yes. So what do we do right now? The range was from 0 to 8. Now the range is from 0 to... Then what did we do? We changed. Which variable did we change? We changed the high. Now the high is 3. The high is 3, and now we do the loop again. We look at the condition of the loop. What is the condition? We wait. No sphere. We look at the condition of the loop. We enter the loop. We have the low is 0, high is 3. We calculate the mid. 0 plus 3 divided by 2. 1. Are you 19? No. Is 19 smaller than you? No. غير ذلك, 19 must be bigger. So the range was from 0 to 3. Now it's from 2 to 3. So what did we change here? We changed the low. Me, mine. So what we're doing inside the loop is we are simply changing the high or the low. This is what we are doing inside the loop. So here, we say else if the value is smaller, if 19 is smaller than a mid, which is right at the beginning. So we found the mid is 4. Are you 19 right here? No. Can I make this on? Nope. Are you 19? No. Is 19 smaller? Yes. So what do? We change high. We make high 3. But what do we do? High equals mid minus 1. Mumtaz. High equals mid minus 1. غير ذلك, let's say that we're looking at the beginning, we're looking for the value 60. Are you 60? No. Number 4. Are you 60? Index 4? No. Is 60 smaller? No. Is the number 60 bigger? Yes. غير ذلك, it's bigger. So what do we change? The low. Low will be mid plus 1. Low will equal mid plus 1. So, Shabab, this is not even a code I need to give you. If you understand this mantiqiyan, you can write the code, as I'm doing with you right now. You have a question? Yeah. If you understand the problem, the code comes directly. If you understand the problem. So now everything is done illa what? The condition. So what is the condition of this while loop? Let me ask you this. Let me do one more example. And I want you to tell me the condition. We do one more example. We say, let's pick a number we don't find. How about pick the number 40. Okay, we're looking for 40. So let's do it quickly. I'm writing on the class. I won't write on the board. So at the beginning, low is 0, high is 8. What is mid? 4. Are you 40? No. Is 40 smaller? 40 must be bigger, idan. So we're at the ghoradalika, the else. 40 is bigger. What do we change? The low. Low is now mid plus 1. Mid count of 4. Low is now mid plus 1. 5. So we do the loop again. We come to the while loop. We do the condition. And we say, okay, this is the low is 5. High is 8. What is the mid? 5 plus 8, 13. 13 divided by 2? 6. So now 6 is our mid. Are you 40? Is 40 smaller? It's bigger. So we change the low again. Low is 7. Low is 7. High is 8. Are you with me? So now we do the condition. We look at the condition again. The condition will be true. We enter and we say, what is the mid? 7 plus 8, 15. 15 divided by 2 is 7. And we look here. Are you 40? Is 40 smaller? Yes, 40 is smaller. So now we need to change what? The high. So the low is 7, but we're saying 40 is smaller. The high is what? 8. But right now we're at 41. 41 is the mid. So are you 40? No. Where is 40? If it's mawjood, where's 40? Smaller. So we need to change the high, right? So what is the high going to be? Mid minus 1, according to the code. So now what will the high be? The high will be 6. But the low will be 7. That's a problem. Mimai? And that's the alama, that's the signal, the sign. Stop the condition. Stop the loop. While what? That's fine. Maybe I'm stubborn. I like to do it in the order, ascending order. While what? Change it. While low. While low. Smaller. Equal. High. Okay, because they could be equal. It's possible you could calculate it where the low and the high were the same, and you still run your program. But here, as long as the low is smaller or equal to high, keep doing it. But at some point, if you get where the low is 7, and now the high was 8, but we say arba'in is smaller, so now the high is 6. So we have a condition where that 6 is small, 7 is the low, is smaller or equal to high 6? No. Quit. So this is what we're doing. And so if we exit the loop, we have one more thing. If we do not find it in the loop, what do we finally do? Return false. Are you with me? Now, if you want to make it a little better, you should make this an int. So what do we change now? Return. Well, here, if we don't find it, we put -1. Tayyib. Read mumtaz. Because it is the index, but what index? The index where we find it. So if we return true right here, what does that mean? That means that value is found at index mid. Imai? Because we said al-hadaf, return the index where we find it. So we return, because mumkin talib yas'al, why do we return mid? Because al-hadaf, we want to return the index where we find it. So here if we say if value equals a mid, this means that we found the value fain at index mid. Okay? Done. This is the code. Clear? Easy. So we come back, and you can now, this is the same code we just did. Does it look the same? I'm looking at it very quickly. Ah, mashallah. I even did the comment too. Nice. Whoever programmed this one did a good job. Mashallah. Allah yafadha. So, comments. Okay, it returns Boolean. I said works just fine. If you want to return integer, you could do the same thing, returning an integer. Okay? So here we go, return the mid. This is exactly what we did. And I had not looked at it since last semester, but you should be able to code it. It's the same thing. Okay? You should be able to duplicate it. So all we are doing, at the end of every loop iteration, what are we doing? Just changing low or changing high. Change low, change high. So this is what happens. Look from here to here. Change low. بعدين change high. بعدين change high. بعدين change low. Find it. So at every iteration, what is iteration? At every step of the loop, at every iteration, what are we doing? We are dividing the search space in half. We are removing 50% of the possibilities. This makes it very fast. How fast? We examine. Okay? So the efficiency of binary search. We say, I want you to see how many comparisons are required if you run an algorithm on n items. How many comparisons total? This is the question. If I give you an array of size n, how many comparisons are required? What I mean by comparison, we look at the linear search. Linear. If n is 100, and we want to know how many, we're looking for the value 12. We start at index 0. Are you 12? No. This is the comparison. No. Are you 12? Aswal hal. Are you 12? No. Comparison. 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 Hatta index 99. Are you 12? No. So how many comparisons did we do? 100. Or n, which is better. We did 100 comparisons on our mithal, or in general, we did n comparisons for linear search. Now for binary search, how many comparisons are required? This is the question. What do you think? If you know the answer because you studied before, do not say. How many comparisons? If n is 100. The usual answer students will say, well, 50? It's not, because it's not 50. So how many comparisons? Let us analyze. If n is 100, after one guess, how many items are left? 50. After two guesses, how many left? 25. After three guesses, how many left? 12-ish. Right? After four guesses, we have 6 items left. 5 guesses, 3 items left. After 6 guesses, we have basic 1 item left. And on the 7th, after the 7th guess, we have finished. Either we found it or we did not find it. So we must make how many comparisons? 7. We must make 7 comparisons. We find the value. Aswal hal, worst scenario, worst case, we find it after 7 comparisons. Clear? So I can skip this part, you can read this later. This is integer division. We just talked about this already. Yes, and okay. So here I say in general, after one guess, how many items left? Half. N over 2. Like if n is 100, we have 50 left, but n over 2. After 2 guesses, how much is left? A quarter. N divided by 4. Yes? After 3 guesses, how many items do we have left? N over 8. After 4 guesses, n over 16. Yes? Me mine. I want to see if you follow. Hands high if you're with me. Okay. So after 1 guess, we divided it in half. N over 2. N divided by 2 is n over 2. After 2 guesses, we divide this part in half. So n over 2 divided by 2, n over 4. After 3 guesses, we take this number divided by half. N over 4 divided by 2, n over 8. 4 guesses, n over 8 divided by 2, n over 16. this is what we have. After 5 guesses, n over 32. So we want to know, after k guesses, k, after k guesses, how many items are left? This is what we want to know. After k guesses, how many items are left? Okay? I just showed it to you. I was hoping I didn't show it, because I was choosing to write on the board or not. But I want you to ask yourself, do you see a pattern? Because after 1 guess, this many, 2 guess, this many, 4 guess, n over 16, do we see a pattern? If a student is good at math, they can see a pattern. Because I would like to see, this is the hint. The hint is we would like to see the guess number inside this number. So after 4 guesses, we have n over 2 to the 4 guesses left. 2 to the 4 items left. Because 2 to the 4 is 16. After 3 guesses, we have n over 2 to the 3 items left. After 5 guesses, we have n over 2 to the 5 items left. 2 to the 5 is 32. What's after 32? 64. After 6 guesses, we have n over 2 to the 6 items left. Let's see who's like a genius. I'm going to pick someone. Who follows me in تحت الآن? مين معي? After 7 guesses, we have n over 2 to the 7 items left. Yes? Okay. I want somebody to be like Mustafa جدا. After 20 guesses, 20 guesses, how many items left? N over 2 to the power 20 items left. Yes? Yes, that's correct. Then, after k guesses, how many items left? N divided by 2 to the k. After k guesses, how many items left? N over 2 to the k items left. Is this difficult? What is the question I asked you? What was the original question? How many comparisons? We want to know how many comparisons are required to find it. How do we know we find it? If we have 1 item, when we have 1 item left, we found it, we don't find it. We don't find it. Are you with me? So here, we want to know how many comparisons. Ma'ana, how many guesses are required? How many guesses are required hatta we have 1 item left? If we have 1 item left, we're done. So the question is, what is this number k? This is the question. What is this number k? So after k guesses, we know that we have this many items left. The question is, what is this number k? How many k guesses? Okay? So we want only 1 item left. So what we do is we set this equation to 1 and we solve for it. After k guesses, we have how many items left? N over 2 to the k items left. And we know that we want this to be only 1 item left. If 1 item is left, we found it. Okay? Or we're done. How many comparisons? We're done. So we want to know, what is this k? Using the n. Like on our mithal, n was 100. Right? But in general, using n, how many guesses? How many guesses do we need? We said after k guesses, how many items left? N over 2 to the k. So what we do is we set this equal to 1. Why 1? Because 1 item left. That's when we know that we're finished. And we want to know how many k guesses. So solve this for k. How do we solve this for k? The first step is easy. Everybody remembers. You multiply both sides by 2 to the k. Right? We want to cancel this in the denominator. So multiply the top by 2 to the k. And so this can cancel, but whatever you do to one side, you must do to the other side. So now we get n equals 2 to the k. Al-hadaf, we want to find k. Does anybody remember how to find k here? You must take the log of both sides. Many students forget this. This is pre-calculus. I write it on the board very quickly. If you take log of, what's our example? We have 2 to the k. So log 2 to the k, log base 2 of 2 to the k. What happens is this cancels with this baglia, as you say, k. This is just math. So if I say log base 12 of 12 to the 144, the answer is 144. This is how it works with logarithmic, okay? So how do we solve for k? We take the log base 2 of both sides, and we find out, when we do this, we find out that k equals log of n. So if we take the log base 2 here, and the log base 2 here, this cancel with the 2, so k equals log 2 of n. Meaning, you do not have to prove this on a test. You do not have to do that. But I want to show it to you. Okay? I just want to show it to you. But what we just saw is the showing us, explaining to us how we arrive at the following conclusion. That binary search takes approximately log n comparisons. Because this was the question. That's what I asked you. How many comparisons does it take? Log n base 2 comparisons. Well, what does that mean? Remember, we said linear search. How many comparisons? N. If we have an array of size 100, aswal hal, we must look through 100. If the array is size, the famous number I use in this class, 1 billion. If the array is size 1 billion, linear search, aswal hal, 1 billion comparisons. But binary search, it will be log base 2 of 1 billion, which is approximately 30. So if we play a guessing game between 1 and a billion, I can find your answer, if I'm smart, dividing by 2 every time, dividing by half every time, I can find the answer within 30 guesses. Baman. Much faster. Okay, so we talk about this. I very quickly show you a nice little chart. So runs in logarithmic time, log in time, much faster than linear. I say, look at the following chart. Here we say, if n is 8, what is log of n? 3. If n is 1,000, what is log of n? 10. So if 1,000, basically, if I say a number from 1 to 1,000, Baman, we can find it within 10 guesses. If n is, what is this? A million, approximately, 1 million, we can find it within 20 guesses. But if n is a billion, we can find it in 30 guesses. Baman. This is huge. Look at how fast. If I ask you in 202, write code to search for a value, you're going to do a linear search. If the array is size 1 billion, you're going to be like that kid. What's the number? 1, 2, 3, 4. You're going to keep going. It's silly, right? But that's what we do in 202. Write the code to search for a number. Check index 1, index 0, بعدين index 1, بعدين index 2, hatta. Last, right? This is crazy. Right? This is silly. It would take too long. So now we're learning something smart. But is this something so amazing with computer programming? No. The good programs are the programs that often work like you would work in life. In real life, how do people win that game? The little kids who win this guessing game, do they know Java? Do they think about for loops? No, they're just using logic. خلاص, 50, divide it in half. بعدين 25, divide it in half. So the best programs are the ones where we think logically and we try to apply that logic, use that strategy on our code. Okay? So super fast. If you think about, the motivators are too difficult to do. I should remove them. Now we have 14 minutes left, and you might think, oh great, we can leave early, because this will happen at times, but actually, we're supposed to do this lecture today. So in 14 minutes, let me see what we can get done of this. I'm going to go through this quickly. This is a problem. I just want you to see algorithm. This is the last introduction little lecture. Binary search is very important. But this I want you to see an algorithm. So very quickly. 14 minutes. This is the problem. It's called the sorted list matching problem. We have two lists. List number 1 and list number 2. And it's a list of names. First name, last name, not the muhim. Here we say last name. It's a list of names. So we have list number 1, list number 2 of names. Each list is already sorted. So this is alphabetically sorted. This is alphabetically sorted. Within each list, all names are distinct. What does that mean? Within each list, all names are distinct. What does that mean?
Not the same.
Within each list, you will not have any duplicates. So if we have Zahrani in this list, you will not have Zahrani again in this list. Only one time maximum. Now, maybe Zahrani's in both lists, but in one list you will find only the name at least only one time, maximum. The problem is we want to print the names that are the same between these two lists. So here's list 1, here's list 2. Print the names that are the same between these lists. Who's with me? Right? This is a 202 problem. What is the typical way to attack this problem? Because of time constraint, I will not, normally I'd spend 5 minutes, have you, brainstorm. But let me just tell you directly. The typical 202 solution, you do not know binary search. For all of them, it's going to be 2 for loops. We're going to check the list. This is the first list, sorry. I'm sorry to think from your side. This is the first list. And the first name is Ahmed. And we want to check, is Ahmed over here? So we're going to do a for loop and check all of these. Are you Ahmed? 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 No, 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 no. Ahmed's not there. Next one, Bilal. Are you Bilal? Are you Bilal? Are you Bilal? Are you Bilal? Are you? Yes? Okay. Next one. There's another, give me a C or a D. Bandar. What's something? So are you Bandar, Bandar, Bandar? No. And you keep going. So how long will this take? If we have 1,000 names in the first list, and we have 1,000 names in list number 2, how long will this algorithm take us? Wal hal? 1 million. I'm saying how long? 1 million. 1 million what? The better thing, how many comparisons? 1 million comparisons. Right? Because for every name here, we must check every name here. So for Ahmed, we check 1,000 times. Aswal hal. For Bilal, we check 1,000 times. Aswal hal. Mimai. This would be horrible. Horrifically slow. Okay? This is the standard 202 way of solving the problem. Okay? So this is the algorithm. 2 for loops. You can look at this. Everybody should be able to write this code. This is 202. Okay? So, the previous solution did not use one fact that was important. We told you the list was sorted. If the list is sorted, we can do this a little bit faster. Actually, a lot faster. We have 2 more algorithms. But if the list is sorted, we can take advantage of binary search. So here, algorithm number 1, how long did it take? How many comparisons? 1 million comparisons, right? 1 million comparisons. Algorithm number 2, what are we going to do? For every value here, we're looking for Ahmed. Ahmed is here. We want to find Ahmed here. But instead of checking, are you Ahmed, are you Ahmed, are you Ahmed, are you Ahmed? We will do a binary search right here. Okay? We will do a binary search. Mimai. For Ahmed, we do a binary search. Do we find it? Yes or no? For Bilal, we do a binary search. Find it? Yes or no? How long does it take to do a binary search on 1,000 items? It would take log of 1,000. Right? Which is from the chart, from the jadwal, approximately 10. Mimai. So To search for Ahmed will take 10 comparisons. To search for Bilal, 10 comparisons. So how many comparisons total? 10,000 comparisons. Me, mine. Are you with me? I'm doing this quickly. So this is talking about what is a binary search. We just covered that. Okay? I'll just give a reminder if it's on a different day. So, wait. Here's our new code. We want to print our matches from list 1 to list 2. Here's list 1, here's list 2. We want to print everything that is common. So we have a for loop. We iterate from 0 to list 1 dot length minus 1. Right? Another one I need to put a minus 1 on. From list 1 dot length minus 1. We iterate all the way, how many times? Well, if this list is 10, we start at 0 and we go all the way to less than 10. So now this is correct code. Okay? Because if the size of the list is 10, we're going to iterate from 0 to less than 10. That's fine. Okay? So this code is correct. So here we iterate from 0 all the way to the end of the list, and for each one, for Ahmed, we do a binary search of list 2. So here we do a binary search of list 2, and so نستدعي المethod binary search, bin search. We invoke the method, we send the list 2, and we send Ahmed. Look for Ahmed in list 2 using the bin search method that we showed you from before. Mimai. How long will this take? 10. Okay, so if it's true, so if we find it, we just print it. We print Ahmed. Okay? So what this bin search method here was using true. If it returns a true, print Ahmed. Ba'dain, we're at Bilal. If bin search, we look for Bilal in list 2. If it's true, we print Bilal. So how long will that take? 10,000. So 10,000 is much better than 1 million. Yes? Much better. So here is our bin search method find. Here's our fail picture for today. I told you I put human stupidity or fail pictures. Why is this a fail picture? MashaAllah, the hat backwards. So he's got the hat backwards and he's MashaAllah like this. Allah Mustaan. So this is a famous hat fail picture, you know, especially if it's sunny, MashaAllah. But he has to look stylish. But what do we see here in Saudi? It's amazing. No, even when I was a kid, everybody wears the hat backwards. But what do I see here? It's amazing. Like the hat sideways, the hat this way. What is this? It's very popular? Some people? Like American Gangster? MashaAllah. But you should give husn al-dhan. I told it in my class last semester, give husn al-dhan. Maybe he's very Mustafa, very smart. Maybe he puts it sideways because he's walking this way and the shams is right here. And then he's not gangster maybe. Maybe he's just Mustafa. And then he walks back this way, he put it this way, and he walks back to this side to block the side. Mumkin. Husn al-dhan. No, I don't think so. Okay, so some amazing things, but our hat failed. Okay, can we do better in 5 minutes? Yes, we can. We can do better in 2 minutes, but in 5 minutes, we have 5 minutes left. Until now, the solution that we've shown is not logically what you would do in real life. I told you the best programs are the programs where it's just logic. You think logically, and you bring that logic to the program. In real life, if I give you these two lists, and I say, find the items that are the same. Output, print out the items that are the same. Or right now, because of time, just tell me the items that are the same. Who can do that quickly? Yes? Davis? Harding? Simpson. Is that it? Anybody else? Davis, Harding, Simpson. Name? Abdul Aziz. Now, Abdul Aziz, do you think that what he did just now Okay, atoms. Are you atoms? Are you atoms? Are you atoms? Are you atoms? Did he do that? Bell. Are you Bell? Are you Bell? Are you Bell? Are you? Did he do that? Akid. No doubt he did not do that. Did he do a binary search? Atoms. Okay, divide it in half. Are you atoms? No. Okay, divide this in half. Did he do that? No. So in real life, how did you solve this problem?
Checking first letter.
Okay. Tell us.
Checking the first letter in Davis and add them first. There is no A starting from B. Bill, there is only one B. It's Boston. It's not Bill. Then Davis. There's one Davis.
Okay, so we print it. Davis. What next?
Now you jump to H, so we don't use the D on and B. And so here we jump to H again. So it's Harding. Then next.
This is how it works. So in real life, what did you effectively do? In real life, what did you do? Is you kept 2 pointers in your mind. A pointer here, a pointer here. Are these the same? No. Then we basically come down on this side because that was bigger. It was a B. Bell, Boston, is it the same? No. So we decrease, we increment to the smaller one. Davis, Davis, are they the same? Yes. Print it, and now we bring both down. Harding, Duncan, they the same? No. Which do we increment? The smaller. Harding, Duncan, no. Harding, Francis, no. Harding, Gamble, no. Harding, Harding. Yes. Print it. If you find it, you increment both. Jenkins, Mason, no. Mason, Lincoln, no. Simpson, Mason, no. Simpson, Simpson, yes. Who's with me? In real life, this is how you do it. You don't use 2 for loops. You don't use binary search. You just, in your mind, quickly do it with 2 little pointers. So the same thing you would do in code. Okay, and I put here for you the algorithm of how you would do this. You start 2 markers and you move those markers down the lists according to this. We're out of time, so I'm going quickly. So how long would that have taken just now? Aswal Hal. How long did that take? We have one list of size 1000, the other list of size 1000. How long did this take? How many comparisons? Aswal Hal. No, the list was 1000 just now. The list was 1000. So how many comparisons did you make using your method? How many comparisons? Maximum 2000. Right? Right here. I mean, how many comparisons do you make if you look at these 2 lists? Right here. How many comparisons? 1, 2, 3, 4, 5, 6, 7, 8. We have 8 here, 8 here. If you think about it, you've made 16 comparisons as you go down. 8 here, 8 names there. You've compared 16 comparisons maximum. So if you have in names and in names, 2n. Or if it's 1000, it would have been 2000. So in real life, you would have done 2000. The 202 programmer, 1 million comparisons. Somebody who thinks they're Mustafa and they use binary search, 10,000. But in real life, it would only be 2,000 comparisons. Very important to try to think logically and to apply to the solutions. What is this? Not talking about this. To apply the solutions that you would use in real life. So the final thing to summarize today, because I want to say it many times, what is log of a billion? What is log of 1 billion? 30. Log of 1 billion, 30. Huge. So if n is 1 million, no, 1 billion. N is 1 billion. N is 1 billion. How long would this take? The first one would take how long? It would take 1 billion times 1 billion, which is some huge, huge, huge number. Here, using this method, it would have been a billion times log of a billion. What is log of a billion? 30. So 1 billion times 30 would have been 30 billion. Much, much better. Using the third way, it would have been a billion plus a billion, 2 billion. Do we see the power of binary search? Very fast. Any question? Anybody come late? Stop recording. Yes. Anybody come late? Attendance? No?